Okay, year 13, welcome to the final chapter of the course, bringing lots of things together, lots of synopticity in here based on quite a lot of your earlier learning. So we've got electric fields, we've got quite a lot about spectra, the ideas of waves, because medical imaging, although it's just a small part of medical physics, it's all about the big growth area. The future of a lot of medical physics is based around trying to get the best diagnostics of what's going on inside of people. So what we're going to do is look at most of the ways that imaging is formed at the moment in medical physics, the main principles. So we'll look at X-rays, which have been around for a long time. We're going to look at different diagnostic methods, so rather than actually just seeing inside, actually trying to work out what's happening inside. So looking at changes within the body and so on. And then we're going to look at some of the optimal ways around it. Effectively, all of these are about waves. Okay, so we have the section in waves. And one of the biggest things for this is just kind of summarizing it all. A lot of the questions tend to be about comparing, contrasting different methods. Okay, so we'll start off with the original method of them all, which is X-rays. Been around for well over 100 years now, ever since Wilhelm Röntgen managed to use Crookes tubes, which we use for discovery electrons and lots of other things. We use for fluorescent lighting nowadays, etc. By cranking up the voltage, he managed to produce rays that were unknown, and therefore he called them X-rays. We can adjust things around the principle of making them, but basically it's a nice straightforward step-by-step method, but it will, by making adjustments, we can produce generally in medical imaging hard and soft X-rays. Those are the kind of things that you'll often hear in the real world. So it brings in ideas of intensity, brightness, and how to get that lovely contrast in your images between something dark and something light. I should point out, if you're worried, that's a ring on a finger, it's not a growth on his wife's hand. Okay, so what's going on? Well, the simple process is what we're doing is we're going to take the same process we had before for producing photons, which is excitation of atoms. Okay, the only difference with X-rays is they're incredibly high energy. So what we need to do is take something that is bringing energy, which is controllable. So for us, we're going to fire electrons, is the usual method. We could use other charged particles, I suppose, but choosing electrons in this one, if we take their energy by taking away the kinetic energy very rapidly, slowing them down, then that kinetic energy is going to be transformed into photon energy. Okay, so by excitation, as we have with all the other things since year 12 to do with electromagnetic spectrum. The difference with these compared to ultraviolet, infrared and so on is that these are the most difficult to get out. These take quite a lot of force, quite a lot of energy to release them from their ground state and excite them up. So when they fall a long way. They're going to produce a lot of energy when each photon is emitted. Okay, so yeah, shall we say the innermost electrons, when they excite and de-excite to give out the rays, that's what causes X-rays, high energy X-rays. Okay, other than that, the tube is basically the same as a Crookes tube, as the photo above shows in a way. What we're doing is there's several processes going on here. So what we will basically do is we will take a metal that is relatively reactive, gives up its electrons relatively easily, and what we're going to do is heat it up with a filament. So if we take a bulb or a wire and heat it by passing a current through it, then that will heat our cathode. Our cathode will lose electrons. We'll have electrons that will just boil off, as they say unscientifically. So thermionic emission, they become ions by using heat to emit electrons. So thermionic emission. And all those electrons will just gather around here just by sticking on a few volts, tens of volts. It could literally just be a light bulb as the heater. But then what we're going to do is take them and give them energy, so direct their energy. So effectively what we do is we will take, and I'll move this around so we can actually see this easily, we will take a connection from one end, we will, and I'm going to put it well over here where we've got a bit of space, we're going to take an extremely high tension source. I'm going to have a negative electrode at this end, the cathode, then I'm going to repel my electrons away. I'm going to have an incredibly high voltage that is positive at this end, and I'm going to, let's conveniently connect it onto the top there. So we're going to connect it into our giant copper cathode, anode. So our positive anode. How does this work? Well, a light bulb in your kitchen will be about 240 volts. Here we're talking to around about 30 to 100 kilovolts supply. Okay, so that's a very, very high amount of energy. Work done, 30 to 100 kilo electron volts for the energy of each electron as it fires across. When it hits the target material, when it hits the anodes, then we excite the electrons within the atomic structure, i.e. within their orbits, and as they jump up, and then de-excite, so they don't escape. Okay, there's not emitting electrons from here, we're just exciting the electrons, they fall back down within the atoms, and they'll each fall will give out a photon. Not all of them will be X-rays. An awful lot of them will fall down in smaller steps within the atom, and so what we get is lower frequencies. Infrared, an awful lot of energy is deposited as heat, so our target, which has to be quite tough to take the impacts, will be something like tungsten, but we'll embed it in copper. So a very large mass of copper, good thermal conductivity, big mass, temperature rises are going to be lower, etc., and then take that away. Now you will see from the one I have in class, even that would cause that to disintegrate fairly rapidly through the heat and so on. So what we actually have in a physical one is our anode will rotate. So you're heating different bits of the anode as you go through. Gives it time to cool down. But most of the energy of these electrons ends up not as X-rays. They're not very efficient. Okay. As we say down here, probably less than 5% of the energy given by that voltage, that high voltage, comes out as X-rays. Most of it is not. So, bit of detail in there, as I say, give you a lot more to it. The bottom line is we need to kind of think about some little details, because that will link into a few graphs and things we got. So we're going to talk about the target, key word to use. So our X-rays produced when high-speed electrons hit the target, and the target is usually, tungsten. Okay, so very tough material. Now, in terms of the energy, again, don't forget we're still going with, I'm not going to worry too much about it, but we're still going with the photon energy, which is going to be HF. But we're also going to talk about the brightnesses. Yeah, so actually, if we are going to, I should label that up as photon. So if you're talking about the current flowing through the target, here we have a flow of electrons, that is an electric current. Well, current is basically going to release more and more charges, because if you think about that, that's just going to be the number of photons times by HF. Okay, current, rate of flow of charges, each electron will release a photon. So assuming it's 100% efficient, each electron will release one photon of X-rays. It will release other things as well, but we're not going to worry about that. So we're going to talk about this, and this is useful because this basically is the idea of intensity. If we want a brighter picture, then what we need is a larger number of photons. To do that, we need a larger number of electrons. etc. So things we can play around with this is we can change how many electrons are released, okay, and we can also change the voltage between these. So we have our electric field here, which is what causes the electrons to accelerate. Okay, so that's our, as I say, our anode, that's our cathode. They'll jump that way across the gap. So let's just step back from the details a little bit. As I say, there's various other factors that you'll hear about potentially in questions and so on. Given you a lot of the background around this already, but the beam itself, the quality of the beam, how good it is in terms of what you want it for, depends on those wavelengths released. And this is where our hard and soft X-rays come in. Hard X-rays mean they're more penetrating, so they are better if you're trying to see bone and no bone. So you get a big contrast in the shadows formed on the film, or the film formed on your detector, where the photons are being blocked. They're blocking out the photons, so you get a shadow, and where they're not blocked. So hard X-rays tend to be used for skeletal damage, so looking at bones and so on, cracks in bones, breaks and so on. But we can use softer X-rays, longer wavelengths, so lower frequency, lower energy for each one, and so they're not as penetrating. And we can use those to look at more soft tissue, so we can look perhaps where there's a difference between density, we'll always see the bone, but density between muscle and fat and so on. So we can start X-raying soft bits of the body, soft tissue, as well as the hard tissue of the bone. The main difference, how do we get that? Well, it's back to the basics, basic principles of physics. So increasing the accelerating PD increases the kinetic energy of those electrons. This will, as well as making them go faster, will also cause more photons to release. So this increases the intensity, as well as reducing the wavelength. Okay, so we're going harder X-rays. So reducing the wavelength. I should say peak wavelength, just like we had with stars. Peak wavelength was that max wavelength, it said in the astrophysics topic, but the peak of the wavelengths. Okay, back to a similar graph in a minute. The beam current will also increase the intensity. So a high beam current, number of charges flowing across the gap, as I've only got half a sentence there, so let's just bring them together. As more electrons cause more photons to be released. Okay, so those are your basic principles. Turning up the voltage gives them more energy, okay, gives them more frequency, but it'll also increase the beam, so it's a bit of a blunt tool. But changing the current is a little bit more precise, so we can change the intensity much better if we think about the current. But again, it's principles, more energy or just more number of photons. Okay, back to the mathematics of that. So let's just have a little go with that. There's a question here to kind of work it through, and this is your fairly typical setup. So we've got a not very efficient X-ray tube. This one's particularly bad, it's only 1% efficient. I'm going to stick 5,000 volts on it. What are the frequency of the X-rays produced? So the idea is that each electron gains energy, a certain amount of energy, and that's because of EV, work done to the electron. Okay, so if you do work on it, it will gain energy, it will speed up. What will that energy turn into? Well, if you're giving it energy, it's going to go faster, it's going to be kinetic energy. So at the moment, just a sneaky bit to make it easier, that's 5,000 electron volts. Okay, 5,000 volts gives us 5,000 electron volts of energy. Each photon, so that's the electron, okay, however, that's your energy in. Each photon only gets, excuse me, can't spell, gets 1% of the total. Okay, which obviously equals 50 electron volts. Okay, so notice I'm not just jumping in with maths. I could just say 1% or 5,000, but yeah, each photon rather than the electron. So the output only gains 1% of the input. So what does that do? Well, that's not a very convenient unit, so we could have done it at the beginning, but it's easier to do it with electron volts for as long as possible. If we multiply that by the charged electron, that will give us a nice round 8.0 times 10 to the minus 18 joules. Okay, so that's how much energy we have got. Now, keeping it simple, assuming no heat loss, etc, 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 assuming all of that energy is converted, well, what's it converted into? Is converted into your frequency, your photons frequency. So if we go back to over here, I'm going to go with EV equals energy in equals HF. Okay, so just to give you that extra bit, I wouldn't expect that in an exam question, that much detail, which goes to frequency, which is what we're after. So we are after energy over H, which equals 8 times 10 to the minus 18. Notice I've dropped it there, but I do have my more full answer there. Over 6.63, don't forget that, because it is more than one significant figure, times 10 to the minus 34, and that's going to equal 1.2 times 10 to the 16 hertz. Okay, so that's pretty damn high frequency. If we go higher, then the efficiency might change as well. Okay, so we do need to be aware of that. So all we're doing is working it for that value, for those values given to us. Okay, but that's a fairly typical question. Work done by the electric field turns into the kinetic energy of the electron. Only 1% of that kinetic energy gets converted into the photon for various reasons, and then so that energy becomes HF, frequency of that photon. Okay, so fairly typical kind of question. Okay, so if we do all that, we can bring in a bit of revision here as well. What we tend to get is a very stylistic, very characteristic graph, and this graph really doesn't tend to go with almost anything else. This shape, these spikes, and so on. So the Bragg father and son double act, who got Nobel Prizes for work on X-rays, came up with these and the mechanisms to discuss what was going on. So these, very similar to Stefan's fourth law, to Wien's law with astrophysics. We have our optimum energy of photons, so the majority of photons are coming out with this energy, i.e. this frequency, linking back to here. The one we have for Wien's law was wavelength, so again, low wavelengths, or long wavelengths rather, and the very tiny short wavelengths on here, because this effectively is related to frequency. So high frequency is the really short waves, long wavelength, low frequency at this end. And all it is, as mathematicians would call a frequency distribution. So we've got many more coming out here. So that is a heating effect. This basically links in, like Wien's law, to do with temperatures of stars. If we turn up the voltage, we will get a much higher amount. We're getting a much more intensity. Again, basically intensity is number of photons, equivalent to. So much more intense here, lower intensity at higher and lower frequencies, higher and lower energies. However, there's a second process that goes on, and that second process is what gives these spikes. Okay, and these spikes are very characteristic of what's happening within the tube. So, could we break it down? Well, yeah, these are specific energies, these are specific photon energies, these are specific frequencies. These are the characteristics of your electron drop. So excitation of tungsten gives you very definite frequencies, therefore very definite energies. These are characteristics of the tungsten. If you had a different target material, these spikes would be in different places, but these are caused by our electron coming in, striking an electron, exciting it, causing it to jump up and fall back down and emit a photon. Now this diagram's not quite correct because there's a lot going on in this, but basically you're exciting them and they fall back down. This electron goes somewhere, you may end up with it being knocked out, but actually most of the time in a fairly simple straightforward one we don't have this ejected electron, so we don't have photoelectric effect as well. We do, but that's not what's causing these spikes, so maybe ignore that as we do the diagram. Okay, so here we go, de-excitation, dropping down, giving out photons, and that's your characteristic X-rays. However, we have something else happening, and this is known as particle scattering. Now just remind you, these are particles coming in, so they don't necessarily lose all of their energy, and that's what causes inefficiency. So if they were to strike an electron straight on, they'd probably knock it out. Okay, we do get those effects as well in the tube. However, if we give it enough energy and it drops down just enough, there will still be energy on this and they will carry on flying onwards. Now, if it doesn't strike, then you are still exciting the atom. You're exciting the nucleus because the charge as well pulls it all around. You've got momentum exchange between the two, so conserved but exchanged. That shaking of the nucleus is what causes other effects of heating. So within this we're also getting heating effects now known, I'm not even going to attempt it, shall we? Bremsstrahlung X-ray systems, so that we get these secondary effects. They're all still high frequency as well, so that's part of it, but also a lot of it is due to heating. So the crude shaking of an atom and the nucleus within the atom and so on, that's what gives you your general curve. But the excitation and de-excitation gives you your pinpoint characteristic frequencies of the target. And both of these we can tune, as you can see from our graph, by changing the voltage, but also changing how many we've got. So we can increase the peak just by releasing more electrons as well. So different pros and cons. So really kind of key processes going on. I'll just add in plus thermal there just to give you that reminder. There's a lot of heat, 90-ish+% of heat loss. Let's put energy just to make sure that's clearer. But yeah, that's basically it. That's all there is to it. And we've used these systems before when we did wave electron diffraction and things like that. So we've had a lot of practice with this. The mathematics is the same. The only thing is we've included the idea of inefficiency, so we're losing a lot of energy. Okay, but just scale down because you're thinking energy in, the energy out, the photons come out. So we'll leave it there. The second part of this is actually how the imaging tends to work, but we'll leave it and break it up at that point.